Okay, so let's go ahead and look at this. We have our Unit 4 notes that we need to start. Like I traditionally like to do, I'm going to go ahead and write down our quiz dates and the test dates that are correlating with this unit. This is Unit 4. This will be our last unit for the rest of this semester. Okay, so it looks like the quiz, let's see. I'm going to double check and make sure. Is Tuesday, Thursday the same as Monday, Wednesday? No, there's not. Let's look. Tuesday, Thursday, yes. Okay, so if you're Monday, Wednesday, quiz, it looks like Monday, Wednesday, your quiz is going to be on 11/23. And if you're Tuesday, Thursday, your quiz, let's see, looks like it's going to be on 11/24. Okay. Something else that we all need to know is going to be our test. I'm just going to put that up here. The test is going to be the same date for all students. It does not matter which day of the week test. And I'm going to put it right here for all students. It's going to be on 12/4 during your class time. Okay? So please make sure you put your name, get your notes printed out. We've got quite some time till the notes are due, but still, that doesn't mean that you wait till the last minute before you do them, because they're going to be helpful for the homework and the quiz. All right, so let's go ahead and begin. We're going to start on this unit. This unit talks about forces and Newton's laws of motion. Okay, so the first thing is, we talked about the first couple of pages. Let me see, page 1, 2, 3, about 3.5 pages we talked about in class already. So this first part should be a review for you. The definition of a force, okay, is a push or a pull on an object. Okay. There is a force, and I don't know why this is such a big gap here. The variable for force is a capital F, not a lowercase f. Okay. You do need to know the difference between our capitals and lower cases. Force is a vector, and the SI unit for force is a Newton. Abbreviation, a capital N. Okay, so a few things that you need to know. Okay, not only is it a vector, but since it is a vector, it can be represented or shown by using an arrow. And we talked about vectors and arrows already. It says here, draw a vector arrow for the following. We're going to move an object 10 newtons west. Not only do we do the arrow, but we also give the magnitude, which is the number. And if an SI unit is available, we give the unit as well. 3 newtons north. Remember, my arrow size needs to correlate with the magnitude. So 3 Newton arrow must be smaller than a 2 Newton arrow. Okay, and then 5 newtons southeast. My 5 Newton arrow should be bigger than my 3, but a half of my 10. So about this big. Okay, southeast. Now let's keep going. So we talked about this part already. We talked about net force. And the word net force means the sum of all the forces acting on an object, and it determines whether or not the object is, and I don't know why I'm missing so much space, is going to move and the direction, oops, EC, of the object will take. I definitely need to change that for next semester. So we're using the word sum, and mathematically, hopefully you're thinking the word sum is going to be addition. But here, it might be some subtraction, because if the vector arrows are in opposite direction, we might have to subtract them. If the vector arrows are west and north, then we're going to have to SOHCAHTOA. So they're just saying that the net force is the answer of all the forces overall combined. Now, we are not only just talking about north, south, okay, or east and west. Remember where we added or subtracted vectors. And we're not just talking about up and to the right, for an example, and use SOHCAHTOA. We're talking about up, down, northwest, up, down, right, and left, all at the same time. And any other forces that are also acting on that object at the same time. So far we've been talking about one force, two forces. This could be 4, 5, or 6 forces acting on one object all at the same time. Okay? Balance forces. So types of net forces. There are 2 types of net forces, or the answer. 2 things can happen. Number 1, it can be a balance force, which we say that that object's in equilibrium, or number 2, it can be an unbalanced force. Okay? Now, if it's balanced, remember when we talked about this last week, we said that there's 2 things that could be happening. Number 1, it can be staying still, not moving. And number 2, it can be moving, but at a constant pace in a straight line, not changing directions. Okay? Unbalanced force means that one force is stronger than the other, and there is going to be a motion or a movement that's going to happen. Okay? So let's go ahead and look at this balanced forces. It says here, forces that are acting on an object that equal 0 to produce a net motion in no direction or not moving, to simplify that, or moving at a constant speed in a straight line. Okay? And I don't like this or over here. I think a little slash or parentheses would have been better. Right? Net motion is no direction, not moving is what we're trying to say, simplify it. Or it is moving, but at a constant speed in a straight line. Okay? Let's keep going. It says here, well, why don't we go ahead and draw a picture of a balance force? Okay, well, we can here's my picture over here. And I've got a person that's pushing on the wall 30 newtons, and the wall is pushing back 30 newtons. I'm just going to put a little arrow just in case, because you may not know what that is. That's my wall. Okay, so my object, my person is pushing on the wall. The wall is pushing back. Now, it's not pushing stronger because then this person would get knocked over. The wall is just not moving because it's pushing back 30 newtons, and this is an equilibrium or balance forces. You're pushing. Are you stronger than the wall? No, because you didn't push the wall forward or over. And if you were stronger than the wall, then you would have gone forward in that direction. But this person's not stronger than the wall, and the wall is not stronger than the person. If it was, it would knock the person backwards. So they're equal and opposite, and there is no motion or moving going on. Right? Or I've got one person over here. I've got another person over here. And they've got a rope. And one person, this person is pulling 15 newtons. And this person is also pulling 15 newtons. And they're playing tug of war and no one's winning. Okay, they're both pulling and they both happen to be able to pull 15 newtons. Okay, another example would be a car in cruise control or an asteroid in outer space that is moving at a constant speed, but there's no friction to slow it down. And so it's just going to continue to move in a straight line in the same path and not speeding up and not slowing down. It says here, forces in equilibrium are either at rest or maintaining a constant velocity. Okay. We're going to pause here. I know that's a quick pause location, but I've got to pause and I will come back.